So in this video, we'll find the derivative of an equation by using implicit differentiation. So the equation is y equals e to the xy power, and in this case, there's no way to get y by itself. You can try to apply ln to both sides and get ln of y equals xy, and I guess you could divide by y on both sides if you wanted. But then, sure, both y's are on the left, but there's no y by itself. You can't do that. There's no way to do it. You're stuck with needing implicit differentiation in this case. So I'm going to apply d dx to both sides of the equation. So d dx of y equals d dx of e to the x y power. So on the left, this is just the derivative of y, dy dx. And if you want to be really sloppy, you could write y prime, but that's vague. The whole benefit, I don't want to say the whole benefit, but part of the benefit, part of the reason to use this fractional Leibniz notation is that it specifies this is the variable of the derivative. The target is always, you got to say what you're finding the derivative of, but the variable for the derivative is only specified with the Leibniz notation, not with the Lagrange prime notation. So that's why we use that Leibniz notation. Okay, so this equals, well, we're going to be finding the derivative of the outside function, writing that down, and then multiplying that with the derivative of the inside function. So whenever you have e to the u prime, this is always going to be e to the u times u prime. But that's with the Lagrange notation. This is implied to be x is the variable of the derivative, a variable for the derivative. So what I really like to write is d dx of e to the u. This is, well, e to the u, because the derivative of e to whatever is just e to whatever, times du dx, the derivative with respect to x of whatever the exponent was. So in this case, over here, that is going to be e to the xy power. Nothing happens to the inside function when you find the derivative of the outside function, times d dx of x times y. Okay. Now in this case, since this is a product, we're finding the derivative of a product, we have to use the product rule. So as a reminder, the standard form that we've seen this before as is u v prime equals u prime v plus u v prime. So we have to apply that using the Leibniz notation. So dy dx equals e to the xy power times, I'm going to use parentheses to group things together. Well, this is going to be the derivative with respect to x of the first factor being x times the second factor. I'm going to put a box around this so it's a little clearer that I don't want things to run together, plus, well, the first factor x times the derivative with respect to x of the second factor, in this case y. Okay, so I've got dy dx equals e to the xy power times, well, the derivative of x is 1, right? And the derivative of y is dy dx, so I'll write it out that way. So 1 times y plus x times dy dx. Okay. So at this point, we've mostly done the hard work. There's some algebra, but the calculus part is done. Now there is a shortcut we can take. There's something we can do that will make things a little bit easier for ourselves. And I'm actually going to point out later, because you won't always notice these shortcuts. So I'm going to show you how to do it without the shortcut, but we will come back to here and we'll point out what the shortcut was, okay, after we do it the long way. So what I need is, I need to get this dy dx and this dy dx to show up on the same side, and then I'll have to factor most likely to have just one copy of it. I need dy dx by itself. That's what I'm solving for, since I'm finding the derivative. So, I think the most straightforward way to do, well, not the most straightforward way, but ignoring a shortcut, the best way, is to distribute. I'm going to take this factor this multiplier and distribute it onto both of those terms. So dy dx equals e to the x y power times y plus e to the x y power times x times dy dx. Okay. Now I'm going to subtract this entire term because I want to move this over there. I need the dy dx's together on the left. So dy dx minus, I'm going to change the order up here a little bit. The order's not super important, but I'm going to put the x first. X e to the xy power times, if I can write that y a little bit neater, times dy dx, and as well I will change the order of these two factors. I'm going to put the y first. So y e to the xy power. Okay. Now, much like we did in the previous video, I have to factor out the common factor. Both terms have dy dx as a factor, so I need to move that outside a pair of parentheses, or a set of parentheses. When I do that, this term, the x e to the yx will stay where it is. For this term, it's not necessarily so obvious what's going to sit there as a placeholder, but you can always multiply by 1 and nothing's really changing. So that's what will remain. So I will factor out the dy dx, so 1 minus x e to the xy power times dy dx equals y times e to the xy power. And we're almost done. Now that I have one copy of dy dx in the middle of the equation there, I can divide both sides by this entire factor to move it over to there. Okay, so I'm going to divide both sides by 1 minus x e to the xy power. So I will have dy, make that a little bit neater, dy dx equals y e to the xy power, struggling with the y's today, over 1 minus x e to the xy power. There we go. That is the derivative. Again, struggling with the y's. Good enough. Okay, so there we go. That is the derivative. Now, this algebra was a little bit messy. There's a lot of symbols floating around. So what's that shortcut? What would help? Well, I'm going to change colors here, and I'm going to rewrite this equation a bit further down. In fact, you know what? I think I can cheat a little bit. I think this will work. Copy. Paste, running out of room here, but that's okay. And let's say, well, I wanted to change colors, but that's okay. The shortcut lies here with the e to the yx. That's part of what made this so complicated looking, because we have e to the e to the xy power in several places. But remember, from the original equation, e to the xy power is y. That's what this was defined to be. So after I find the derivative, anywhere I see an e to the xy power, I can replace that with y, and that will simplify things a little bit. So I can get rid of this and instead write this as dy dx, bleeding into my next example there, equals y times y plus x times dy dx. So we still have to do more or less the same algebra, but it's going to be a little bit easier for us. It's going to be a little bit easier to see what to do because I don't have that exponential expression anymore. And similarly, right here, both of these guys, I can replace those with y's for my answer. I don't have to leave, even though I've taken the route of having the e to the xy power the whole time. I don't have to leave it there. I can say, well, you know what, this equals y times y would be y squared over 1 minus x times y. And I can clean up my solution a little bit, make it look a little bit nicer. And as far as I know, in the online homework system, this is going to work either way. It should accept either one, most likely. If you put this in and it doesn't like it, try the other one. But I expect either one will work. So that's that example.